Hello everyone, we're going to be talking about, this is your pre-lab lecture for the potentiometric titration of soda ash. Just as a sort of little warning, some of this material, depending on when you're doing this lab, there might be some details here that we have not gotten to in class. That's okay, you can still perform the lab and still interpret it, but you may not fully understand all of the sort of background and nuances of what's going on during the lab. So if there's anything that is that seems out of bounds or that you don't quite get yet or seems unusual, just you can either talk to me about it or you can just be patient and we'll get to it in lecture at some point. So the soda ash titration, we're dealing with carbonate here, and this carbonate is what we call soda ash. Okay, and we're going to be titrating it with acid. Okay, so this is going to be just like we did with the KHP, which we did in the first experiment, but that first experiment, the KHP, was we titrated with a base. In this case, our titrant is going to be a strong acid. So this here, H3O plus, is going to come from HCl, okay, which we all know because it's a strong acid. It dissociates into H plus and chloride, and that this is our titrant. Okay. Alright, we call this our titrant. Alright. One thing you'll notice here, so carbonate can be titrated twice during the process, so it can actually pick up 2 protons. And we'll get into that a little bit later in the class, but I just want to talk a little bit about weak acids and weak bases, right? Because this is called weak acid, weak base titration. And what we're talking about in this case our analyte is a weak base. Okay, so this is going to be a weak base titration. So what we draw this up like is like this. B, in this case, so a weak base, just as you recall, something that's going to react with water and through equilibrium process becomes protonated and produces hydroxide. Okay, and this is described by equilibrium constant Kb. Just like all our other equilibrium constants, we have our products over our reactants. So, right here are our products. Our reactants. In this case, we ignore the water because that's just a solvent. And so this is what our equilibrium expression looks like. Okay, and so just so you know, when we're titrating, what we're actually doing is your H plus that we're going to be adding is be reacting with excess base, excess hydroxide, and neutralizing that essentially. Okay, and so what we're going to do in this experiment is going to be a little different than what we did before, where we use an indicator. In this case, we're going to do something called potentiometric titration. At potentiometric titration, we're going to be monitoring pH as we titrate, and this is what you'll find gives a lot more accurate and precise measurement. All right, and so what this generally would look like, so what we're going to be doing is we're going to be adding a volume of titrant. Okay, in this case our titrant is going to be HCl, or just generically you can just call this acid. Okay. And we're going to start at 1 pH, and since we know that we're starting with a weak base, then our pH should be relatively high. Okay, it's going to be basic. What's going to happen is we're going to add a titrant, and we're going to monitor that pH. What we'll see is that the pH will sort of change gradually, and then we see it drop down really rapidly, and then sort of tail off a little bit. Okay, and so in this process, we're actually going to identify 4 particular regions. Right, we're going to call this region 1. All right, so this is before we've added any of our titrant. There's this other section here, which we're going to refer to as region 2. This is where we've added a bit of titrant, but we haven't got to this big drop yet. Region 3, we're going to see, is going to be right here in the middle, and this is what we call the equivalence point. Right? And then region 4 is basically everything after the equivalence point. I just want to give you some special emphasis on that equivalence point, right? This region 3 here, this is what we call the equivalence point. Okay. And so everything we can think of is sort of in terms of if we're before or after the equivalence point. So I'm just going to talk a little bit about what controls the pH during this process. Now this is where things might get, if we haven't got to this point in class, things might be a little unfamiliar to you. You don't need to know how to calculate all these sort of pHs at this point in the class. Later in the class you'll be expected to know it, but right now I just want to talk about it just so you have a little context for what's actually going on when you're performing this titration. So we're going to go through these sort of step by step. So at equivalence point 1, before the titrant is added, the pH here is really just, let's see, yellow. The pH is really just determined by that equilibrium expression, Kb. If you recall, Kb is, as we showed you earlier, Kb is, it comes from this equation here where we have our BH plus and our hydroxide over our initial base concentration. Okay, and so this pKb, right, this is a constant, right? So you can find this in a table. Likelihood, in all likelihood, you'll go find this in a table, and that, remember, our weak base is going to sort of equilibrate between the sort of protonated form and the non-protonated form. Okay, we showed, if you remember back here, this is what I'm talking about. Okay, so what we can do if we want to determine the pH, we can actually say that every time we form a hydroxide, okay, if you remember from this, right, we form a hydroxide here. Every time you form a hydroxide, you're also forming one of these protonated forms, right? And every time you do that, form one of these, you're also losing one of these, okay, so to keep everything balanced. And so to simplify that, we can say that this is X and this is X, right, because these are equivalent, and this is the formal concentration minus X. Okay, so this whole thing can be simplified as X squared over F minus X, okay, where X is going to be equal to your hydroxide concentration. What you may recall is that pH, and remember pH equals the negative log of H plus. Okay, remember this, and that, it's yellow now, that's another equilibrium constant called Kw, which we're going to talk about in class. We haven't talked about it yet, and that relates H plus to OH minus, the hydroxide. All right, so basically, from this equilibrium constant, we can determine the hydroxide, and from the hydroxide, we can determine the H plus. And the H plus, we can determine the pH. Okay, so this is what dictates the pH at this region right here. Okay, so now we move on to 2. And so in section 2, we've added, look at here, we've added some volume of titrant, but we haven't gotten to this big drop. We haven't gotten to the equivalence point. So this is before the equivalence point. And this part we call the buffer region. Okay, so if we think about our reaction, we got our base plus water, right, goes to, again, pH plus OH minus hydroxide. All right, so what we're doing is when we add our titrant here, which in this case is H plus, right? That didn't change. So we add our H plus. What's going to happen is that's going to react with hydroxide. And as that happens, right, because of Le Chatelier's principle, we're going to be forming more of this. Right? So this is going to increase, and this is going to decrease, right? And so what's going to happen is that's going to drive the reaction this way. All right, and so another thing we're going to talk about in class, if we haven't done so already, is that under this is going to be controlled by the Henderson-Hasselbalch equation. So if you have not seen this before, Henderson-Hasselbalch looks like this. Your pH in a buffer region is controlled by the pKa and the log of your acidic form over your, log of your basic form over your acidic form. In this case, this is going to be B over your protonated form. Okay, and so what we're doing is as we add more acid, more of our titrant, what we're doing is we're shifting this ratio. All right, so we're increasing the denominator here. All right. Okay, and so what ends up happening is we end up decreasing the pH overall, and we end up with, so basically this value becomes smaller and smaller, and so the log of it becomes more and more negative, and so we end up decreasing the pH. So we shift it down, so it starts moving down towards these more acidic regions. All right. So what you're going to see as you're monitoring the pH, you're going to see this gradual decline, and then you're going to see a big jump. All right, and that big jump is going to happen at the equivalence point. All right, and the equivalence point is where essentially at the equivalence point we've added exactly enough acid so that you have a 1-to-1 ratio. So volume of H plus is let me do that again. So concentration of H plus added is going to equal your formal concentration of your base. All right, so you're in a 1-to-1 ratio here. This is 1-to-1. Okay, and so in this case, what this ends up looking like, it's as if you made a solution that was just BH plus. Okay, and so BH plus here, all right, our protonated base, this is just a weak acid. And so our weak acid, in this case, will be dictated by a pKa, or a Ka, I should say. I'm going to cut that out here. Let's do that. So in this case, Ka is going to describe this reaction here, where you have BH plus goes to B plus H plus. Okay, and so this equation is going to look like this: B plus over BH plus. Okay, and just like we saw before with the base, this can be simplified into saying x squared over f minus x. In this case, our x is here, x equals H plus. Okay, and as we know very well at this point, that our pH is just the negative log of our H plus. All right, and so this way we can determine what our pH is, and this is totally dictated by this Ka here. Okay, so that's at the equivalence point, right? So now we're here, and now once we go beyond the equivalence point, it's essentially like you've just added a bunch of acid to your solution. So after the equivalence point, and we're going to get this a lot more detail in class, this is just dictated by pH is dictated by the amount of excess acid that we've added. Okay, so hopefully that sort of makes sense to you guys. So we start this region here, right? We have our pH that's determined by the Kb of our weak base, we start adding some acid, we get into the buffer region. We're dictated by the Henderson-Hasselbalch equation here. We reach the equivalence point where now it's like we just made a solution of weak acid, and so our pH is dictated by the Ka, and then after that we're just dictated by the excess acid that we've added. Okay, so again, you guys aren't going to be expected to calculate all this at this point in the class, but I just wanted to give you this information so you know what's going on in the experiment. And what we want to do, right, is find this equivalence point. Okay, because at this equivalence point, we know that we've added enough acid, so we're at exactly 1-to-1 ratio here with our base, right? So we find the equivalence point, we'll find exactly how much of our weak base we had. And so the easiest way and most clear way to do that is to do these derivative plots. And so if you look at the derivative of your of this curve here, okay. So the first derivative is just going to be basically the change in pH with the volume of titrant. And what you'll see is we have a maximum change at some point, and you get something that looks something like that, right? And at this maximum here, this is where the rate of change of your pH is the most. And this is actually going to be, if you look at the volume here, this is your equivalence point. I'm just going to call this EP. Okay, this is your equivalence point. So that's one way to look at this. The other way to do this is to do actually a second derivative plot of this. And this, in this case, we end up with something that looks a little bit different, right? The second derivative plot is centered around 0, and you get a plot that looks a little funky, and it kind of shoots up, and then back down, and then back to 0. All right, and so the point here, where this is passing, right? So this is your 0 line. You can find really precisely where this passes through. Where this passes through 0, and this is also your equivalence point. Right, so these are just two different ways to find the equivalence point by plotting the derivative of the data, right? And this data you're going to get is by monitoring the pH while performing a titration. And one thing I wanted to mention is that, you know, the example I showed you, it was titrating a weak base with a strong acid. But you can actually imagine that we would find we could do the exact same thing if instead of acid we titrated with a base. If we started with an acid, right? So if we did a base, then we just do the exact opposite. So it actually, if you started with a weak acid, you'd start with a low pH. You'd go through a buffer zone. You'd see a huge increase, and then tailing off. And again, you would get equivalence point. Right, and so this is just the this is just another way of looking at it. And again, we're not going to be doing this in our class, but all the principles that we're doing this titration can be thought of in terms of the other direction. Okay. And so in the case of soda ash, if you recall, this was actually a diprotic system, so we can actually add. So here would be one equivalent, and we can add a second equivalent. All right, and so you're just going to get a titration curve that looks just like the previous one, but there's actually going to be 2 steps to it. And so in this one, we're going to end up with, right, again, you end up, so you start out at 1 pH, a high pH, come to a buffer region, hit one equivalence point, tails off again, in another buffer region, then you're going to hit a second equivalence point. You're going to look something like this. All right, and again, now in this case, you have 2 equivalence points, right? And so I want to emphasize that these equivalence points that we're looking at are actually volumes here. And you're going to have equivalence point 1 and equivalence point 2. And at equivalence point 1, your titrant and your analyte are going to be 1-to-1. At equivalence point 2, your titrant and your analyte are going to be 2-to-1. Because at this point, you've protonated, right, this second site right here. And just like I showed you before, we can do a derivative plot, and this comes out of your textbook here. In this case, you notice we're starting at a low pH and going to a high pH, right? And you see the titrant here is sodium hydroxide, so we're titrating a weak acid with a strong base, and we see two equivalence points. They may not be super clear where they are on this regular plot, but if you plot a first derivative, you see these two maxima. If you plot a second derivative, you see it pass through 0 here at 2 different points, here and here. And what happens is, and what you guys are going to do in this lab is you're going to make these plots and you're going to plot them in Excel. And if you zoom in real close, alright, let me give you a second here. So this is how we make these derivative plots. So this is directly out of your book. You can look at this. So this, what you're going to do when you're doing your titration, you're going to record your volume of sodium hydroxide, right? So you're going to be adding, and this is going to be off of your burets, just like you've done before. And you're going to be measuring the pH here. This is going to be measuring the pH meter. Okay, so this is the data that you're going to get from your experiment. You're going to put this in Excel, and then you can essentially follow these instructions right here. And it'll show you how to make a first derivative plot, and then how to make a second derivative plot. Again, this is page 216 in your book. Alright, so I will ask you to refer to that when making these plots. And then you'll get a plot that looks something like this, but again, remember yours will be sort of opposite direction of this, because this is, you're going to be doing a weak base with a strong acid. And if you zoom in here, so this is what this little box here is showing you, you're zooming in, looking at, trying to figure out exactly where this crosses, you can actually get a real good indication right here of your equivalence point. So again, this is going to be equivalence point 1, and this box right here just corresponds with that. That's equivalence point 2. That's 2. Alright, so you're going to be able to find a very good indication of the amount of soda ash you have in your experiment. And just like we did with the KHP, your soda ash is actually in a mixture, and so you're going to determine the weight percentage of that mixture. And so the plan for the lab is, first, you're going to make and standardize a titrant. In this case, the titrant is HCl. This can be just like you did with the sodium hydroxide, alright, except you're going to use a slightly different indicator. We're going to use bromocresol green. You're going to do pretty much the exact same thing you did previously. You're going to use a standard that you know, and then you're going to titrate it, and you're going to use that primary standard to make a secondary standard of your titrant. Then I'm going to give you an unknown. You're going to measure that mass by difference like you've done before. And then you're going to perform potentiometric titration. So this part is actually going to take a long time, because it takes a long time for the pH meters to stabilize every time, because you're going to want to make a pH measurement at every point along your titration. And then after that, you're going to have your data, and you're going to bring it back, put it in an Excel spreadsheet, plot it, do those derivative plots, and determine the equivalence points. And from those equivalence points, you're going to be able to determine the amount of soda ash, and from that, you're going to determine the percent composition of your unknown. So with that, I'll see you all in lab on Tuesday.